In this section, we're going to look at speed of a wave in a string. The speed of a wave in a string, let's say I have this string over here. If you excite this end, that wave is going to travel along the string like this. Now, how fast that wave travels depends on two factors. It depends on the tension in the string, that's how tight the string is, the tension in the string. It also depends on the density of the string, depends on the density, that's mass per unit length, the density of the string. Okay. Now we're going to use mu for the density, which is the mass of the string divided by the length of the string. Okay, so it's going to be the density or mass per unit length of the string. This is mass per unit length, mass per unit length, and let's use T for tension in the string. Tension in the string, that is how tight the string is. And of course we're going to use V for speed. Okay, so the dependence between speed and these factors is the speed is proportional to the square root of the tension in the string. It's also proportional to the inverse of the mass per unit length. Actually, with constant proportionality 1, we have the following formula. The speed of a sound in a string equals the square root of tension divided by mass per unit length. Okay, so this is a formula for the speed of a wave in a string. When, let's say, one end of the string is excited, the wave will travel with this speed, and that speed depends on how dense that string is and how tight that string is. The tighter the string, the greater the speed, and the smaller the density of the string, the greater the speed. Now let's look at the following example. Suppose we have a string. A string has, let's say, has a length of maybe 1 meters. Okay, and then let's say the tension is provided by hanging object. The tension in the string is provided by a hanging object, let's say of mass 10 kilograms, and let's say the mass of the string is maybe 20 grams. The mass of the string is, let's say, 20 grams. Okay, now the question is, calculate the speed of a wave in the string. Calculate speed of a wave. Okay, so let's write what we know. This is the situation we have. We have, let's say the string is clamped over here. Let's say it's the table over here like this. Okay, and then we have the string over here. Maybe there's a pulley over here, and then we have a hanging object over here. We're saying the mass of this one is 10 kilograms. Okay, and the length of the string as a whole is 1 meters. The mass of the string is 20 grams. Okay, so the question is, when this end is excited, how fast will the wave travel along the string? Okay, and first let's calculate the tension. The tension string over here, this object is in equilibrium, it's hanging, right? Therefore the tension is balanced by the weight of this object, okay, which is mass times gravity. So since it's at rest, the tension equals to the weight of this hanging object, mass times gravity. So the tension is mass times gravity. The mass is 0.02 kilograms, and then this is 9.8. Okay, so this would be 0.196 newtons. Okay, all right, so we have the tension. So now we can calculate the speed. The question is calculate the speed. The speed is square root of tension divided by the mass per unit length. The mass per unit length of the string is the mass of the string divided by the length. Okay, so that is 0.02 kilograms divided by 1 meter. So that's 0.02 kilogram per meter. Okay, so with this, the speed of the sound is square root of 0.196 newtons divided by the mass per unit length, which is 0.02. Okay, so this is approximately 0.2. So that's probably approximately equal to the square root of 10. All right, and that is approximately equal to 3.3 meters per second. So, well, the string is very thick, that's why the speed is very low, but this is a very slow speed for a wave. All right, now we're going to look at standing waves. Standing waves. A standing wave is a wave with equal spaced points of zero vibration. This is a wave with equally spaced points of zero vibration, You might have noticed it, for example, let's say you have a rubber band. If you've noticed it, a standing wave looks something like this. Okay, there are points of zero vibration separated by equal distances. Okay, so what this means is the molecules here are vibrating vigorously over here, but there are molecules that are equally spaced that do not vibrate. Okay, these points of zero vibration are called nodes, and these points of maximum vibration are called antinodes. Okay, so what we call a standing wave is a wave with equally spaced points of zero vibration, and the points of zero vibration are called nodes, and the points with maximum vibration are called antinodes. Now, you see there's a wave traveling over here. The wavelength of that wave is related with the size of this loop. Actually, one loop is equal to half of the wavelength of a wave. So, one loop of a standing wave is equal to half of the wavelengths of the wave. Okay, let's say so we can say that one loop equals half of the wavelengths in the standing wave. Okay, so one loop equals half of the wavelengths traveling, the wavelengths of the wave that's traveling in the string. Okay, now we're going to look at harmonics. First, we're going to start with harmonics of a string clamped at both ends. Clamped at both ends. Okay. Now, for a given length, there are only certain wavelengths that can give rise to a standing wave. Okay. The first one will be the one that has only one loop. Okay. So this would be the first harmonic, or is also called the fundamental harmonic. So this one corresponds to the first harmonic. It is the harmonic with only one loop. Okay. Now suppose the length of this string is L. Okay. So what we have is one loop. The size of one loop equals the length. Okay, the size. But one loop is half the wavelength. Okay. So let's put a 1 over here to indicate that is the first harmonic. So lambda 1 divided by 2 gives you the length of the string, and then the wavelength that gives you one loop in this string is twice the length. So a wave with a length of twice the length of the string will give you one loop in the string. Okay, and this is called the first harmonic or fundamental harmonic. This is the first harmonic or fundamental harmonic. Now let's look at the second harmonic. For the second harmonic, we have two loops. Okay, let's say still have the same length over here, but we're going to have two loops like this. Okay, so if the length of the string is L, the size of two loops equals the length, right? So you get two loops equals the length, but one loop is half of the wavelength. Okay, so twice. Now we're going to use the wavelength of the second harmonic divided by 2 gives you L. Okay, so from this you get lambda 2 equals L. So the wavelength that gives you the second harmonic is equal to the length of the string. Okay, let's go to the third one. For the third one, you're going to have three loops like this. Three loops. Okay, so in this case the length is still L, so we have three loops. The length of three loops equals the length of the string. Okay, so you've got 3 times lambda 3, that is the wavelength for third harmonic, divided by 2 equals to the length. Okay, now from this you get lambda 3 equals 4 over 3L, and so on. Okay, now let's try to generalize for n loops. If you've got n loops, then we're going to say n times lambda n divided by 2 equals the length. Okay, all right, so that gives you the wavelength of the nth harmonic equals twice the length divided by the number of harmonics. Okay, so generally the wavelength is twice the length divided by the harmonics. Okay, the number of loops. Okay, so this is the wavelength of the nth harmonic, and n is the number of loops. So lambda n is wavelength of the nth harmonic, and n is number of loops. Okay, now let's look at the frequency. The frequency is speed divided by the wavelength, right? We use F for this one. So F is the speed divided by the wavelength. Okay, so the frequency of the nth harmonic is the speed divided by the wavelengths of the nth harmonic. Now remember, the speed depends only on the tension and mass per unit length, okay? So it will be a constant for all the harmonics as far as the tension in the string is kept constant, okay? But we just concluded that the wavelengths of the nth harmonic, you see, in this section over here, is twice of the length divided by the number of loops, twice of the length divided by the number of loops. So with that, we've got the frequency of the nth harmonic equals the speed divided by 2L divided by the number of harmonic. So we get this is number of loops times speed divided by 2L. Okay, so the frequency of the nth harmonic is given by V over 2L times N. Okay, now let's find F1. When N equals 1, we have F1 equals V over 2L times 1, which is V over 2L. Okay, so this quantity over here is the frequency of the first harmonic. So we have the following recursion formula: Fn equals, this is the first frequency, N times F1. So if you know the frequency of the first harmonic, you can reproduce the other harmonics very easily using this formula. The second one is twice, the third one is 3 times, and so on. So the frequency of the nth harmonic is simply N times the frequency of the first harmonic. Now we're going to look at sound resonance in pipes. First, we can consider a pipe open at both ends. Sound resonance in a pipe open at both ends. Open at both ends. Okay, so we have the following situation. In this case, we have the pipe, okay, like this. Okay, now the molecules are free to vibrate over here. So at this end we're going to have an antinode, at this end we're going to have an antinode. Okay, so the first possibility, that's the first harmonic, would be with antinode over here and antinode over here, would be this one. Would be this one. You see? So how many loops do we have? We've got half loop, still one loop. Okay, so if the length of this pipe is L, then we got half loop plus half loop is one loop. So you've got one loop equals the length of the pipe. But half loop is half of the wavelengths. This is the wavelength of the first harmonic divided by 2 equals L. So you get lambda 1 equals to L. Okay? If you take the second will be something like this with antinodes at both ends. This is the second possibility, like this, like this. Okay, so what do you have? Half loop, 2 loops plus 1 loop. I mean half loop plus half 1, 1 plus 1, 2. So you've got 2 loops is equal to the length of the pipe. Okay, so that is 2 lambda 2 over 2 divided by L. As you can see, the formulas are exactly the same like the formulas for a string clamped at both ends. So generally, for n loops, you've got n loops times the loop, which is lambda n over 2, gives you the length, and that gives you the wavelength of the nth harmonic is twice the length divided by the number of loops. So as you can see, the formulas for the case where we have a string clamped at both ends and sound resonance and a pipe that's open at both ends are the same. So that also follows Fn would be V divided by lambda n, and that gives us NV over 2L. But V over TL is F1. You see, F1 equals V over 2L, and that follows Fn equals n times F1, just like the case for a string clamped at both ends. So the formulas for the case where you have a string clamped at both ends and you have a pipe open at both ends, the formulas are the same. And then we're going to look at sound resonance in a pipe open at one end, closed at the other. Sound resonance in a pipe open at one end, closed at the other. Okay, so in this case we have the following. You have this pipe, it's open at one end but open at the other. So what's going to happen is over this end the air molecules are free to vibrate, so we're going to have an antinode at this end. But over here the molecules are not free to vibrate, so we're going to have a node. Okay, so the first possibility will be this one. So this is the first harmonic. So in this case we have half loop equals the length of the pipe. Okay, half loop equals the length of the pipe. So that is half of, and one loop is lambda 1 over 2 equals the length, and that gives us lambda 1 equals 4 times L. Okay, so the wavelength of the first harmonic is 4 times the length for the case where the pipe is open at one end and closed at the other. Let's look at the second. The second is going to be like this, and then we have to have node over here and tin over there, so it'll be something like this. So we have one loop and a half, that is 3 over 2. So you've got 3 over 2 loops equals the length of the pipe. Okay, this is L over here. So what we have is 3 over 2 times, this is the second harmonic, lambda 2 over 2 equals L. And what do you get from here? You've got lambda 2 equals 4 times L divided by 3. Okay, let's look at the third one and then we'll generalize. For the third harmonic, we're going to have something like this. Okay, so we have 2 full loops and a half, that's 5 over 2. Okay, 5 over 2. So 5 over 2 loops equals the length of the pipe. Alright, but one loop is half of the wavelengths, right? We got L over here, so we get the wavelengths of the third harmonic. The wavelengths of the third harmonic would be 4 over 5L, would be 4 over 5L. Okay, now let's generalize the nth harmonic. Okay, that is n loops. If you've got n loops, no, not n loops, the nth harmonic, you see the first one is half of a loop. The first one was half of a loop, right? We can write it as 2 times 1 minus 1. The third one was 3.5. We can write it as 2 times 2 minus 1, right? The third one is 5 over 2. We can write that as 2 times 3 minus 1. So generally, for the nth one, it's going to be 2n minus 1 divided by 2. Okay, so for the nth harmonic, following this pattern, number of loops equals 2n minus 1 divided by 2. Okay, so the number of loops, 2n minus 1 over 2 times one loop, which is lambda n over 2 gives you the length of the pipe. Okay, so we have lambda n equals 4 times L divided by 2n minus 1. Okay, so this is the wavelength of the nth harmonic. The wavelength of the nth harmonic. Okay, now let's look at the frequency. For the frequency, we have the frequency of the nth harmonic equals the speed of the wave divided by the wavelength of the nth harmonic, right? So that would be the speed divided by 4L divided by 2n minus 1. So you get the following formula: Fn equals 2n minus 1 times the speed divided by 4L. Okay, now let's look at the first harmonic. So you get this general formula over here. Now if you look at the first harmonic, we've got F1 equals 2 times 1 minus 1 V over 4L, which is simply V over 4L. Okay, so it's this expression right here is simply the frequency of the first harmonic. So we have the following general formula: the frequency of the nth harmonic is 2n minus 1 times the frequency of the first harmonic. Okay, so the frequency of the nth harmonic equals 2n minus 1 times the frequency of the first harmonic. Now let's consider an example. Suppose we have a pipe, let's say of length 2 meters. Of length 2 meters. Okay. Let's say calculate the wavelengths of the third harmonic. Okay. If you want, you can use the general formula, but just like this. The third harmonic would be something like this. Okay, that is 5 over 2. That's 2.5. So you've got 5 over 2 loops, which is lambda 3 over 2 equals the length, which is 2. Okay, so you've got lambda 3 equals 4 times 2, 8 over 5 meters. Okay, and then let's say if the temperature, let's say is 20 degrees centigrade, calculate the frequency of the third harmonic. The frequency of the third harmonic. Okay, so now we have the wavelengths. All we have to do is calculate the speed. So you've got F3 equals the speed divided by lambda 3. Okay, but for the speed we have the temperature. Okay, so the speed equals 331 meters per second, square root of 1 plus 20 divided by 273. Okay, that's approximately 343 meters per second. Okay, so the frequency of the third harmonic is going to be the speed 343 divided by the wavelengths 8 over 5 or 1.6. Okay, and that's going to be hertz. All right. Next we're going to look at a beat. A beat is a wave with points of zero vibration separated by equal time intervals. This is a wave with points of zero vibration, points of zero vibration separated by equal intervals of time, equal intervals of time. Okay, this is like a drum, you know, you got boom, zero vibration, another boom, zero vibration, another boom, zero vibration. If those zero vibrations are separated by equal time intervals, the wave is called a beat. So the difference between a standing wave and a beat is that a standing wave is points of zero vibration separated by equal distances, while a beat is a wave where the points of zero vibration are separated by equal intervals of time, just like a drum beat. All right, so graphically you might draw a beat like this. So let's say you've got this beat over here, then comes to zero, then we have another beat over here and drops to zero, another beat over here, and so on. So this is one beat, second beat, third beat, and so on. Okay, so that's what a beat is. We have boom over here, zero vibration, boom over here, zero vibration, so on. That's what a beat looks like. So how is a beat formed? A beat is formed when two waves of very close frequencies interfere. A beat is formed when two waves of close frequencies interfere. Okay, now the number of beats heard per second is called the beat frequency. Beat frequency let's use FB. This is number of beats per second. Okay, per second. Remember, this is 1 beat, 2 beat, 3 beat, and so on. Okay, and it can be shown that the beat frequency simply is the difference between the two interfering waves. Let's say the beat is formed if the beat is formed by two waves of frequencies F1 and F2, and the beat frequency equals simply the difference between the frequencies of the two waves. So this is a formula for a beat frequency. The beat frequency is simply equal to the difference between the frequencies of two waves that interfered to give the beat. All right, and of course beat period is the time interval from here to here. Okay, this one is the beat period. Okay, and the beat period obviously is going to be the inverse of the frequency of the beat frequency. So let's say this is beat period, which is time taken for 1 beat, and we have TB equals 1 over the beat frequency, or 1 over the difference between the frequencies. The reason we have absolute value is because, you know, the difference could be negative, so that's why we have to put it in absolute value.